Hello Internet, my name is Quinn and this is Blondihacks. My journey continues to build the eccentric engineering tool sharpening system. We're going to work on the angular track assembly that runs along the top of the table. Your guess is as good as mine what this is for, but it's pretty neat, so let's build it. Here's our workhead so far, you may recall. You may or may not recall that there's a groove on the underside of the workhead, and that rides on this kind of track mechanism that sits along the top of the work table. This is called the angular guide assembly, and it's what we're going to build today. Now, it doesn't fit in there yet, of course, so we have a fair bit of work to do and a whole bunch of other little parts to make. There's actually quite a few parts in this assembly. Starting with the track itself, though, I'm going to fixture it on a scrap of aluminum to act as a spoil board, kind of a sacrificial parallel. That's a good type of setup for long, thin parts like this that can be difficult to fixture. There's a dimple in one end that's for a mounting bolt. I'm going to drill that straight through, not bothering to line up on it particularly well because precision is not super important for the location of that hole. The dimple is enough to guide the drill to vaguely the right area. Now I can use that hole along with a thread that I tapped in the aluminum block to fixture one end of the track, and you can see that I've drilled and tapped a couple of other holes as well to fixture along the length. And this is going to allow me to access both edges of the track for machining without having any clamps in the way. Now I got to dial this in mostly straight. We're going to be fully cleaning up both edges, but I want it to be pretty close to straight to start with so that I don't machine it all crooked or run out of material to clean up before I get under dimension, that sort of thing. The surface is laser cut and fairly rough, but we're within a couple of thousandths. That's going to be fine. Then from there, we've got a full millimeter to remove off both sides, so if we're mostly straight to start with, then it's going to end up just fine. So I make a couple of cuts down both sides. Again, the end mill is just touching the aluminum, so that I am cutting into the aluminum a little bit to guarantee that I get a full cleanup cut along the sides of the steel. But honestly, the damage to the aluminum is pretty minor, and when this is done, this piece of aluminum bar just goes back in the bin, and it's still perfectly usable for some part in the future. Obviously, you don't want to do this to your mill table, which is why I'm using a spoil board like this, but you don't have to think of this as wasting the piece of aluminum that you use this for. You hardly even touch it, honestly. I'll do a test fit with the workhead. I want to make sure this is a reasonably nice sliding fit on there. And that seems pretty good. I'll check it in a couple of spots to make sure, but so far so good. I think we're at least in the ballpark. With simple parts like this, we can always do a little bit of fettling with a file later if we need to improve the fit, but I think that seems good. Now to machine the center of the track, I'm going to shift my clamps one at a time so that nothing moves to the outside of the piece of steel. So I'm clamping the steel and the aluminum kind of all at the same time, and that will allow me to remove all of my fixturing screws from the center of the track. So now nothing has moved because we changed one clamp at a time, musical clamps as I like to say, and now I can machine the inside track of this thing. There's actually two different slots required to be cut here, and of course both are metric, and I don't have a lot of metric end mills, so I'm going to have to make do. So I'm going to start by cutting a smaller slot right down the middle, which is supposed to be 5mm, so I'm using a 3/16 end mill, which is a little bit smaller than that, and I make one cut right down the center, and then I make a couple of light passes down either side to widen it out to 5mm. And yeah, that center clamp is close, but in machining, clearance is clearance. Clarence. Don't call me Shirley. Funny story, while getting ready for this cut, I was going through my metric end mills, and I do actually have more of them than I thought. However, I do not have matching metric R8 collets for all of them. So I have a couple of metric end mills that I cannot hold in my mill because I don't have metric collets in every size that I should have. So I gotta add that to the shopping list, I guess. Metric R8 collets. And I really need a 5mm end mill. I also probably need metric gauge pins, but at least for gauge pins you can do pretty well with an imperial set because there's always going to be something that's very close. So I am using an imperial gauge pin to check for a 5mm dimension all the way down. That's actually a little bit small. This gauge pin is undersized, so that's a little bit snug, but again, I think I'm going to leave it here because the threaded fasteners that slide in this slot seem to be moving nicely, and I would rather leave it here and have things be on the snug side, and I can always, as I said, fettle them later if needed. Now we come in with an 8mm end mill, and I'm going to go down part way through the material, and we're going to make kind of a shelf we're effectively making a T-shaped track inside here. I decided to do this with one cut, which was a little bit aggressive for this mill based on the amount of material being removed all at once here, but yeah, this is a very sharp brand new end mill. I've got a nice rigid setup, and I had a pretty slow feed, and it seemed to work okay. Fun fact, 8mm is one of those R8 collet sizes that I'm missing, but this is a 5/16 R8 collet, which is within a couple thousandths of 8mm, so I got away with it. The joys of machining in Canada. You kind of have to have two sets of tools. That should be it for the milling on this piece, so I'm going to take it down. Now you may have noticed that there are rounded ends on this track, and we've machined the sides of it down narrower. Now it was laser cut with the radius appropriate for the oversize width that it had. So technically now those end radii don't line up anymore. There's kind of a step. There's a discontinuity because the radius of the ends is now larger than it should be. So a person could, I suppose, set that up in the rotary table and mill those ends down, but that would be a lot of work for what's really a very minor cosmetic discontinuity. So instead, I'm just going to blend it all together a little bit on the Scotch-Brite wheel. I'm constantly amazed how many problems in the machine shop are instantly solved by the Scotch-Brite wheel. Here's the final track piece now. Pretty pleased with how that came out. It's a nice looking part. And the handles that come in the kit should slide nicely in there. Next up are a couple of large beveled washers, and the kit includes these fiddly little laser cut discs of hot rolled plate for the purpose. However, making beveled washers from those is a whole lot harder than just turning them out of some steel round bar. So that is what I'm going to do. I'll put those little discs, I guess, in my steel bin, and who knows, maybe I'll find a use for them someday. But for now, let's go straight to the round bar and turn these washers. The main feature of interest on them is that there is a large bevel on the tops of them just to make them look nice. So I can do that all in one cut because this is free cutting steel that I'm using. This is 12L14, which machines really, really beautifully. Even on a small lathe like this, I can go straight in with a chamfering tool and create quite a heavy, aggressive bevel all in one cut, as long as I run very slowly. I think this is about 80 RPM. L14 is really nice steel to machine. It does have a tendency to rust very easily though, so you got to protect it. Next up is a hole through the middle. Now we actually have two of these washers to make. One has a 4mm hole and one has a 5mm hole. So I'm making the 4mm one first for a reason that, I don't know, I thought was kind of clever, that you'll see in a moment. I drill that hole through and now I can part it off. And Yahtzee. Now the part that I thought was clever. The 4mm drill left a dimple after the parting, which I can now use to center the 5mm drill, which is of course larger, to drill out the second one. Saves me center drilling and possibly other setup. Sometimes I have a good order of operations idea. Not often, but it does happen. Here are those two beveled washers now. Pretty nice looking parts, very simple, but very machiny looking. And those ridiculous discs that would have been very difficult to use to make those. You can see how these guys are going to sit on top of the track. Next up is a clamping piece for the end of this track to clamp it to the table, and the kit includes this half-moon piece to make that from. And yeah, this thing's got kind of a cool, rocky, back and forth kind of motion. It's almost like a scale rocking horse for a duck, hypothetically. Yeah. That's pretty fun. All right, Swarfy, that's enough. We've got work to do. No, we talked about this. Come on. You had your fun. All right. 5 more minutes. Then we've got to make this part. I need that piece of steel. This part is going to be pretty quick to make because there's not a whole lot of precision or accuracy required for it. So for example, I'm not going to get out the edge finder and try to line up perfectly on that hole. I'm just going to line up the drill by eye, rotating it 90 degrees so that the flutes will deflect a little bit and tell me where I'm misaligned. This will get you close enough to where you can drill through, and that dimple is going to put the hole in basically the right place. If there were other features on this part that had to be exactly the correct distance away from that hole, then I might be more concerned about getting the DRO lined up on the desired location of that hole, but again, not a lot of precision required for this part. There's really only one dimension that has to be super accurate, and that's the little shelf that we're going to cut after drilling and tapping this hole. More on that in a second. Now I can flip it up on edge, and I'm going to machine the long side of this piece. And again, not a lot of precision required here. I'm just going to use my digital level to get the laser cut surface level so that I'm removing approximately a level cut across the top of it. But again, if this was a little crooked, it really wouldn't matter. It would just mean that the half circle was sitting, 1 degree off, but I don't think you could even tell. So that's enough accuracy there. The nice thing about that is that once I've got that skim cut done, I've automatically got my 0 on the vertical dimension, so now I can bring the cutter down to the right depth for the little shelf feature that we need to cut. And this is the one dimension that needs to be fairly accurate, because this dimension needs to be just a little bit thinner than the table so that we get a clamping action from the underside of this. This will all make sense when you see how it goes together, but this depth of the slot is really the only critical feature. And honestly, even this, it's got a 0.1 millimeter tolerance, I believe, which is plenty of wiggle room in machining. The curved profile on the back remains laser cut and unfinished. It's not a critical feature for anything, but I did decide to clean it up a little bit on the Scotch-Brite wheel just to make it look nice. Once again, Scotch-Brite wheel, the problem solver. Hashtag not sponsored. Time for more test assembly. Let's see if things are going well. If I did that right, then there should be a little bit of a lip between the edge of the table and that piece, which there is. I can catch my fingernail on the edge of the table, which means that the table is just proud of the surface of the top of that clamp, which is good. That means that when I thread these pieces together, it will actually clamp the pieces together. If the top surface of that clamp was proud of the table, or even possibly even with the table, it wouldn't clamp very well, or possibly not clamp at all. But that works beautifully. One thing I've learned in this project is the secret to a really nice feeling clamping mechanism is to have just a little bit of a clamping distance, like a very small but definitely non-zero clamping distance is how you get a clamp that doesn't require a lot of motion on the clamping arm, but feels really good. Next up is this little piece which clamps the other end, and again the kit supplies this slightly ridiculous laser cut chunk of hot rolled plate to make it from. And once again, I'm going to ignore that and turn it out of this piece of round bar that I got in my bin. This is a mangy old chunk. I think it's from an old eccentric that I turned on a steam engine, but this is why you never throw anything away, because it's just the right size to squeeze this little piece out of. I'm actually going to start by facing, more or less facing one end, and turning this end down all the way to 3/4, which is actually smaller than the final part. What I'm actually doing is creating a mandrel on the back of this stock, with which I'm going to use to hold the part for all the subsequent operations. It'll make sense in a second why I'm doing this. Once I've got a diameter that I like there, now I'll flip it around and hold that mandrel end in the chuck and actually create the part. Once again, start by facing off the end, as is tradition. And then I'll turn the OD of this down to the desired 20 millimeter that this part is expecting. As I do this, you can imagine what it would be like to try and use those little laser cut discs to do this. You'd have to somehow hold this tiny little part, find the center of it, drill a hole through the center of it, then make a tiny little mandrel to hold it on the lathe so that you could turn the OD of it, and then we have all the milling features to cut in it, so we'd need some way to fixture this tiny thing laying flat on the mill in order to cut all these little shelf features in it. All of that would be really difficult, whereas as you'll see, with this little setup that I'm about to do, all of this is really quite easy. Starting with a thin disc part is really only a good idea when you have no other choice, such as a casting for a cylinder head or something like that. I've done all I can on the far end of the part with the lathe. However, we've got a bevel that goes on the top edge of the part, and that's on the chuck end of the part. But I can still do that from this setup before taking it down out of the lathe. I can do that by going in a ways with my parting blade, but I'm not ready to Yahtzee it off yet. I'm just creating a starting groove. And then I can come in with my chamfering tool and actually create the chamfer on what will become the top of this part after we've parted it off. And we could do this later with a second setup, but You'd lose some concentricity if that mattered, but more importantly in this case, that would be a lot more complex than just doing it now. So we've got plenty of room, we've got the material to just create the bevel in situ right now, and then we can take it down and do the rest of the features. So with that bevel now cut, I've still got a groove left at the bottom that I can come back into with my parting blade later, because I've established that that's the top of the part. But now comes the secret sauce of this order of operations. I can take this out of the lathe, go over to my mill, and put that little mandrel that I turned in a collet block. That's why I had to turn it down a little bit so that it would fit in a collet that I have. And I can set it up vertically in the mill in this collet block and cut all the little shelf features in the end of this part very easily. For maximum precision, you could indicate in the collet block vertical at this point, but honestly, for this part, just setting it up with my good square is going to be good enough. Now I'm going to use the high point of the outside of the curve as my reference, and that's a stunt that I can do because I have the Heimer, which is a combination of dial indicator and edge finder. So I can wiggle back and forth on the y-axis and find the high spot of that curve, and then start my x-axis edge find from that point. So I can create a valid reference from the outermost tangent of that circle. And this was a good thing for me in this case because that is how the drawing was done, so it made it easy to get all my dimensions. But let's be honest, the Heimer is an expensive toy for a hobbyist that I only have because it was a gift. If I was going to do that with a traditional mechanical edge finder, then I would center up, which is easy to do on any curved surface with a traditional edge finder, and then it just means you have to adjust all the dimensions on the drawing to be referenced from center line instead of from one end. One little tip about this setup, you'll note that I'm cutting on the y-axis, and that's so that the cutting forces are against the vice jaws. I have had parts move when cutting in a setup like this on the x-axis, because on the x-axis you would be relying strictly on the friction of the jaws, which sometimes is not enough. I scrapped a part once that way. There's the clamping shelf. Once again, the dimension on that was pretty important because that's going to determine how smoothly it clamps. And we have another very shallow shelf that's cut along the top. And this creates a clearance to create a kind of toe clamping or strap clamping action on this piece. I'll show you how this works when it's done because it's pretty neat. But for now, just know that I need to create a very shallow cut. And again, this is all pretty easy because of this setup. I can't imagine, again, trying to do this with those tiny little discs of laser cut hot rolled plate. Yeesh. Then back over to the lathe to part it off. If I had additional turning operations to do here where concentricity was important, then I could at this point dial it in on a 4-jaw chuck or use a collet chuck to regain my concentricity, but here I'm just parting off, so not a big deal. There is that final piece. It's a really nice looking part actually. It's pretty simple, but it's very clever in its design. I want to show you how this thing actually works because it's a great lesson in mechanical design if you're designing these kinds of things for yourself. Once again, the table is slightly proud of that clearance that we cut, and that's important so that we'll get a clamping action, which after test assembly we do indeed. Once again, the secret to a really smooth and pleasant to use clamp is having just a little bit of clamping distance between the pieces. That's beautiful. It clamps tightly but doesn't require a lot of handle motion. Very nice. Let's take a look at that clamping piece from underneath because it's really neat how this actually works. On the far left of the part, it's full thickness there, so there's kind of like a foot there, if you will. That's sort of the heel of a strap clamp like on the mill. And then in the center is a little clearance, that very shallow shelf that we cut. And that's underneath the screw that's doing the clamping. Again, just like the center area of the strap clamp on a mill. And then way out here on the right edge is the thinnest area, and that's where the actual toe of the toe clamping is happening. Keep this shape in mind if you ever want to design your own clamps. You always have to have these three elements. You've got the heel, the clearance area underneath the threads, and then the toe area where the clamping is actually happening. Next up is a T-nut that rides in that track that we did at the top of the show. I'm just going to zip through this because it's not super interesting. It's actually the same order of operations that we just used for that little clamping piece. Same technique of leaving myself stock on the back on the lathe so that I can throw it in a collet block vertically in the mill and cut some straight sides on it to create the T shape that's needed to ride in that track. Hopefully you can see how this works here. Pretty nifty little piece, actually. I'll do a little in situ deburr because I want to test fit it on the track before I take it down out of this setup. I'm trying to make sure all these pieces move together smoothly, but that's a little bit tricky because I don't actually fully understand how all of this mechanism works, so I don't know how snug or how loose things should be. So I'm kind of keeping everything on the snug side, and I can fiddle things later if they need to move more smoothly. But once again, I'm pretty pleased with how that little T-nut came out. These little parts are often the most attractive and most satisfying to make. I don't know why. That slides in there again. It's a little snug. It might need some loosening up, but I'm not sure yet until I really understand how this all works. There's something called a tool block that bolts to this T-nut and slides along the track, but the workhead also slides along this track. So again, not totally clear how this all works. We're going on this adventure to figure it out together, but that is all the time I have for the project this week. We're in the short rows on this one. We just have another handful of parts to make, and we're going to finally get to see how this thing allegedly sharpens tools. I'm excited. I hope you are too. Thank you very much for all of my patrons who make all of this content happen every week, and I will see you next time.